Today we will be dealing with fundamental of convection, and this is the unit number 3, and this is the first lecture of unit number 3. So these are the objectives of our lecture, and you can see these actually cover the entire chapter of this unit. Okay, so the objectives of the current lecture are to understand the physical mechanism of convection and its classification, visualize the development of velocity and thermal boundary layer during flow over surfaces, distinguish between laminar and turbulent flow, and gain an understanding of mechanism of momentum and heat transfer in turbulent flow. Derive the differential equations that govern the convection on the basis of mass, momentum and energy balances, and solve these equation for some simple cases such as laminar flow over a flat plate, etc. And then non-dimensionalize the convection equation and obtain a fundamental form of friction and heat transfer coefficient. Use analogies between momentum and heat transfer and determine heat transfer coefficient from the knowledge of uh, friction coefficient. So the mechanism, if we want to understand the mechanism of convection, as you can fundamental mechanism of convection, as you can see from this these three figures, as you can see these first two figure. Okay, so the conduction and convection both require the presence of material medium, but convection requires fluid motion. Convection involves fluid motion as well as heat conduction. Heat transfer through a solid is always by conduction. Heat transfer through a fluid is by convection in the presence of bulk fluid motion, and by conduction in the absence of it. So if there is no fluid motion, then the heat transfer is through the conduction only. But when the fluid motion is present, then the heat transfer is through the as you can see is called the convection. So therefore conduction in a fluid can be viewed as the limiting case of convection and corresponding to the case of quiescent fluid. Okay, so as you can see in the case A, and in case A and in case B there is a fluid motion, and in case C there is no fluid motion, so there is no convection. Okay, so the heat transfer in case number 3 will take place only through conduction. So now let us understand the physical mechanism of convection. Okay, fluid motion enhances heat transfer since it brings a warmer and cooler chunk of fluid into contact, initiating higher rates of conduction at a greater number of sites in a fluid. The rate of heat transfer through a fluid is much higher by convection than it is by conduction. So as you can see, the higher fluid velocity, the higher rate of heat transfer through the convection. Okay, as you can see, if there is a fluid, this is a hot plate and this is a cold plate, so heat transfer through sandwiched between parallel plates in the presence of fluid can be, as you can see, can be approximated like this. So the physical mechanism of fluid convection, as you can see, let us further discuss the physical mechanism of fluid convection. So the convection transfer is strongly depends on fluid properties like dynamic viscosity, like thermal conductivity, like density and specific heat, as well as the velocity of the fluid. Okay, so whatever fluid, like either liquid or gas, the heat transfer through convection depend on these quantities. So as you can also see that it also depends upon the geometry and roughness of the solid surface through which the liquid and gases are in contact. In addition to this, the type of fluid flow, such as in streamlined or turbulent, I mean in the present type of flow like streamlined, laminar flow or turbulent flow. So convection also depends upon the types of flow. Okay, so as you can see, this is the Newton's law of cooling that we have earlier discussed. the Q heat transfer rate per unit area uh, due to convection is equal to H Ts minus T infinity, and if we multiply this in Newton's law of cooling with area, then we will get the this equation. So heat convection, H is called the convection heat transfer coefficient, and its unit is watt per meter square per degree Celsius. And A is the area, Ts is the temperature of the surface, T infinity is the temperature of the fluid sufficiently far from the surface, and it is also measured. Here it is measured in degree Celsius. Okay, so the convection heat transfer coefficient H, as we have discussed earlier, it is the rate of heat transfer between a solid surface and a fluid per unit area per unit temperature difference. And there is one more condition when a fluid is in direct contact with a solid, so it sticks to the surface due to the viscous effect, and this condition is actually called the no slip condition. And these are also again important when it comes to the convection, and then convection also depends upon the boundary layer. Okay, convection is different in the boundary layer, and convection is different, convection rate is different on the layer which is other than the boundary layer. So the flow region adjacent to the layer in which viscous effects and thus the velocity gradient are significant is known as the boundary layer. So the fluid property responsible for the no slip condition and the development of boundary layer is viscosity. The development of boundary profile due to the no slip condition as the fluid flows over a blunt nose. This actually, this figure shows this. As you can see from the no slip condition, that this is a plate. On this plate a fluid is moving on this plate is stationary, and it comes at the complete stop at the surface because of the no slip condition. Because of the no slip condition, here the fluid which is at the with the contact of the plate is actually has zero velocity. Okay, and as you can see from this figure, as the velocity uh, dis, uh, as the distance from the flat plate increases, you will see that the velocity goes on increasing, and after some time it becomes almost equal to the approach velocity. Okay, almost equal to the approach velocity, but the velocity at the contact surface is zero. Okay, velocity here is zero. So as you can see, this is how the velocity across the velocity varies with the distance from the plate. So the heat transfer coefficient that we discuss here has implication of no slip condition, and heat transfer from the solid surface to the fluid layer adjacent to the surface is by as you can see at the is by pure conduction, since the fluid layer is motionless and can be expressed as by this relation. Okay, q convection equal to q conduction, that is equal to minus k of the fluid into del t over del y, and at y equal to 0. Okay, so this is the heat transfer per unit area. So this is and the mode is conduction. Okay, because of the presence of you can see no slip condition. And as you can see, when we want to find out the convection heat transfer coefficient, here this is the value of convection heat transfer coefficient. So the convection heat transfer coefficient in general varies along flow or in along x direction. The average or mean convection heat transfer coefficient for a surface in such a case is determined by properly averaging the local heat transfer coefficient over the entire surface AS or length L, that is equal this is given by this relationship, as you can see by integrating this equation and finding the average of this equation, we will get the average or mean convection heat transfer coefficient. Okay, so one more important thing that has come from this slide is that the heat transfer coefficient is not a fixed quantity, it is not a property of material, but it depends upon many factors. So this is the man who discovered a number that is called the Nusselt number, and he was a he was a German engineer and was born in Nuremberg, Germany, and he studies machine. This is the man who discovered the Nusselt number. So as you can see, this is the meaning of Nusselt number. Nusselt number actually describes the ratio of convection to the heat transfer by conduction. Okay, this is the Nusselt number. So in convection studies, it is a very common practice to non-dimensionalize the governing equations and combine the variables which group together into dimensionless numbers in order to reduce the number of total variables. So that this Nusselt number is also a dimensionless convection heat transfer coefficient. Okay, and it is given by this formula HLC upon K, where L is the characteristic length, K is the thermal conductivity, and H is the heat transfer coefficient. So Q convection is H delta T, and this is equal to Q conduction equal to K delta T upon L. So by taking up the ratio, we get this Nusselt number formula. So heat transfer through a fluid layer of thickness L and temperature delta T is given like this. So the Nusselt number represents the enhancement of heat transfer through a fluid layer as a result of convection relative to the conduction across the same fluid layer. The larger the Nusselt number, the more effective the convection. So higher Nusselt number indicates the good convection heat transfer, and the Nusselt number of equal to 1 for a fluid layer represents the heat transfer across the layer by the pure conduction. Okay, so Nusselt number cannot be less than 1, it is always greater than or equal to 1. Okay, for a Nusselt number which is equal to 1 means that the heat transfer is taking place because of the pure conduction only. Okay, so if we want to see some examples of convection in our daily life, most of the time we encounter lots of you can see lots of cases which involves convection. For example, as you can see in this case, sometimes what happens that blowing on the fluid on the food, when the food is very hot, what happens that sometimes we blow on the food so that it gets a little bit cold. Okay, so this is one such example, or you can say a funny example. Apart from this, we turn on the fan on hot summer days to help our body cool more effectively, and the higher the fan speed, the better we feel. We stir our soup and blow on a hot sliced pizza to make them cool faster. The air on windy winter days feels much colder than it actually is. The simplest solution of to heating problem in electronic packaging is to use a large enough fan. Okay, so this is the summary of today's lecture. We learned that convection is expressed by Newton's law of cooling. Okay, and we learned about the Nusselt number, which is a dimensionless heat transfer coefficient and is defined as Nu equal to HLC upon K. Okay, where H is the heat transfer coefficient, K is the thermal conductivity, and LC is the characteristic length. So these are the review question that you have to you try to find out the answer. Okay, they are these are some basic question like define the incompressible and compressible fluid, and what is the forced convection, how it differs from the natural convection, is natural convection caused by the wind forced or natural convection? Okay, so these are the questions that you have to the answer of these questions you have to find out. What is the external force forced convection, how it differs from the internal force convection? Can a heat transfer involve both internal and external convection? Okay, so all these are some of the questions that you have to go through. These are the references through which this PPT was created. And thank you for this lecture. Thank you all.